Good morning, everybody. So I'm from University of Washington, and we have a group there that we call the N-body shop because we deal in N-body codes, both collisionless codes, that is where the particles are only interacting via gravity, and also smooth particle hydrodynamics codes where we include hydrodynamic forces as well. And so I'm going to spend this first hour talking to you just about how we do N-body codes. This is more in general, I say protoplanetary disks, but I'm one of those cosmologists as well that desperately needs some more information about how stars form. So there will be but the interesting thing is we actually use the same code to do protoplanetary disks as we do for cosmology. Partly that means that the physics we put in is a bit simpler than, say, in Ramsey's or other star formation codes, although we are developing more sophisticated physics modules. So again, this morning I want to talk about tree codes in general. I want to start off by talking about why N-body is a good way to go for astrophysics. Talk a little bit about solving gravity, which is an extremely hard problem and involves, in our case, multipole expansions and how that fits into a tree algorithm, which is how we organize the particles. And then talk about how we integrate forward in time. And then finally, I'll end up talking about just an overview of how smooth particle hydrodynamics works. Okay, so what is the N in N-body? Lately, it seems to be N is the number of authors on the papers, which as codes get more complicated, we get longer author lists. But within the code, what we're trying to do is take a continuous distribution of matter, perhaps, and we're representing it with a collection of particles. So in this case, the particles are a sample of the mass distribution. And so generally when you sort of naively, when you first think about N-body simulations, you're thinking about something like the solar system, where each particle is a discrete body. It has interactions with the 9 or 8 other bodies in the solar system. This is not exactly what we're doing here. Okay, what we're trying to do is model a continuous distribution. And therefore, these particles are not individual bodies, so to speak, but they're samples of a distribution function. And this distribution function could be distribution both in position and velocity, which means we're talking in general about a 6-dimensional space which we want to resolve. And this is doing a 6-dimensional grid simulation could be extremely computationally intensive. And one way to make that somewhat simpler is to random sample this distribution both in position and velocity. And that's a good motivation for, so you think of those particles as random samples of that distribution function. One thing that buys you right away is if you're sampling the mass, then just because you're following the particles, you're explicitly conserving mass. So that's something that you instantly get out of using this kind of technique. Okay, and again, let me emphasize, because we're sampling a distribution function, the number of particles that we have is not talking about the number of real particles in the universe or in a protoplanetary disk. And this is supposed to both the case for cosmology, where we're doing dark matters. The number of dark matter particles is like 10 to the 80. We can only fit 1 billion or so particles in our computer, so there's a big mismatch. So are we doing the right thing with such a small number of particles? Well, you have to think about it correctly, right? You have to think about these particles as samples and not the individual bodies. I'll talk a little bit more about that later. Okay, so we've got a collection of particles for which we want to integrate the orbits due to gravitational and hydrodynamic forces. How do we go about this? Let me talk about tree codes and why I'm a tree hugger. And the point is that the universe is big, okay? All right, the joke is, it's a long way to Safeway from here, but that's peanuts compared to the size of the universe. I start here with molecular cloud cores, which are of order slightly less than a parsec. If we want to study how that turns into stars and planets, eventually we have to resolve down to things that are fractions of an AU. Plug in the numbers, and you get a crazy amount of grid cells to resolve three-dimensional space. And furthermore, I decided here to start with molecular cloud cores, but as we heard, I was just at a Protostars and Planets conference last week, and I learned that the star formation people actually need the cosmologists to set up the initial conditions, right? Because star formation happens in this differentially rotating galaxy, and so the scales I really should start with are kiloparsecs or even bigger, okay? It's the kiloparsec and plus scales that sets the initial conditions from which your giant molecular cloud does its dynamics, which ends up with molecular cloud cores, all right? And you'd like to somehow encompass both the galactic scales as you're trying to form your stars and planets. So a huge range of scales and a very diverse set of geometrical configurations. The cloud core is spherical. It's actually in a galactic disk. It collapses into another disk, the protoplanetary disk. The planets, again, are spherical. Perhaps you have multiplicity in your star formation. And so something that can adapt to all those different geometries in a natural way is very compelling. And a tree code has the ability to do that. So that's motivation. Let's get into a few more details here. Solving gravity. All right, I said gravity is a hard problem. You're trying to solve this differential equation, partial differential equation here, Poisson's equation, relating the Laplacian of a gravitational potential to the mass density, and of course it's the gradient of this potential which will give you the forces which are applied to the particles. Okay, this is an elliptical partial differential equation. That's a statement about how the boundary conditions influence the solution. And in particular, you need all the boundaries to determine a complete solution. That is every point in your solution space depends on every other point in the solution space. So you got to solve them all at once. This equation is actually, in some sense, very simple in that it's a linear partial differential equation. And so you can apply all the power of linear algebra to obtaining solutions. You might think that's a trivial statement, but if you tried to work with, say, modified gravity, the resulting partial differential equation is significantly more complicated. But linear algebra tells you that if you have a linear equation and you can identify eigenfunctions of that equation, so that is a function for which when you take the Laplacian, gives you an eigenvalue and returns the function back again, then you can easily construct solutions by expressing your density in terms of those eigenfunctions, and then you just divide by the eigenvalues, and you solve the equation. It turns this into an algebraic equation that's easily solved. And probably the most familiar example is Fourier transforms. So if I take the Fourier transform of the density, I can easily just divide by k squared, and that gives me the Fourier transform of the potential, inverse Fourier transform, and I've solved it. Fourier transforms work if your boundary conditions are cubical, and so you have a cubical grid. If you have a spherical grid, you can use spherical harmonics as eigenfunctions. But if I have an arbitrary points in space, as a tree code would give me, I can't easily do this eigenfunction decomposition. And so I have to work a little bit harder in solving Poisson's equation. By the way, please, all right, this is a school, okay? You're students, you're meant to ask questions, okay? So please stop me. You want me to go in a little further detail, right? That's why you're sitting in the room and not watching this on YouTube, okay? Well, some of you will be watching this on YouTube later, okay? Right. Okay, so Poisson's equation again. Let's look at this not in its differential form, but in the integral form, where the potential is this integral over, so the potential at a point x is an integral over the mass distribution at point x prime over an entire volume, and of course weighted by the 1 over r gravitational potential. And if we have n particles, then this mass distribution is actually a sum of delta functions. The mass is concentrated at the points located at positions r sub I. So this is what the density is, and you plug that into here, and the delta function integral of the delta function gives you this sum. And this is why I need to evaluate the potential at each point I, and that involves a sum over every single other point. And so if I have 10 to the 9 particles, then I have 10 to the 18 terms in this sum. Okay? So that is generally undoable unless you only have like 10 to the 5th particles or so. So we need to be a little bit smarter. I like to go to those eigenfunctions, but we can't do that. What we do instead is figure out how to evaluate this sum a little more cleverly. Yeah? Well, it's both. Yeah, so, yeah, thank you. I sort of missed that note here. All right, so you see the problem with this sum. There are these infinities there as you approach individual particles. And so we can't just do this sum. We'll have to modify gravity such that as you approach individual particles, the potential doesn't go to the infinity, and neither will the force go to infinity. And so we'll modify the 1 over r force law such that it goes to some, so that the potential goes to some finite value when x equals x prime. Okay, and that I might say a little bit more about that later, but that goes along with the idea that these particles are not individual bodies. All right, they represent some portion of phase space, which you would consider to be smoothly distributed, not a delta function. Yeah, and thank you for that question. Okay, so how do we do this? A little more cheaply. Well, we take advantage of the fact that as we get far from a mass distribution, we can actually express the potential as this sum, where well, you have G, where these are the spherical harmonics. So that's a combination of Legendre functions in cosine theta, and then circular functions in phi. And the L and M, that's the order in theta and the order in phi, divided by r to the L plus 1. And all right, if you take this sum to infinity, then this is an equal sign. If we truncate this sum at some finite L and M, then this is an approximation. And the point is that if x is greater than the maximum value of x prime, then the terms here, these CLMs, divided by r to the L plus 1, well, you have this r to the L plus 1, which means that these terms will scale as this ratio, so you see as L gets large and x is large, these terms get very small. And so we can truncate this expansion, and you have some small error term. And we characterize the error by something we usually term theta, or an opening angle. And I'll explain why we use the term opening angle in a second. But that's essentially the size of the mass distribution we're interested in, divided by the distance we are from the center of that mass distribution. Okay, so if we're way out here, we can consider the gravitational consequences of this mass distribution as the first few terms of this spherical harmonic expansion. Okay, so I'm assuming that people are familiar with spherical harmonics. Now, right, I've expressed this in terms of spherical polar coordinates, r, theta, phi. It turns out to be more computationally efficient to express it in terms of Cartesian coordinates, x, y, z. Unfortunately, the algebra gets considerably more messy. But, sorry, I'm having a hard time with position here. But here's the first 1, 2, 3 terms of the expansion. We usually refer to this as a monopole term. And you can see that what this first term essentially means that assume that all the mass in that sphere was placed at the center of mass. What would the gravitational potential be? Well, it would be, if you do the integral, you see integral of d cubed rho prime of x prime, rho of x prime. That's just the mass divided by the distance. All right, so that's force from an individual particle placed at the center of mass of that entire mass distribution. Higher order term, we refer to this as the quadrupole term. That's a dipole term. You see that we're integrating, so we're integrating over x prime. We're finding the dipole moment of the mass distribution. And over here, this is the quadrupole. We're finding the second moment of the mass distribution. And this expansion continues on. Like I said, this is more complicated expression than Legendre polynomials, but it's much quicker to evaluate. And so this is the preferred way to evaluate the multipole expansions. And therefore you can get, with just a few operations, the potential at a large distance from a collection of mass. I should also point out that you can speed things up by, once you do this multipole expansion, you can convert that into a local expansion around a point where you want to calculate the forces via spherical harmonics. But this is, you can see it's r to the L. A local expansion is essentially a Taylor expansion of this function around some point where you want to calculate your forces. So you can imagine we've got one collection of particles where which are the sources, and I calculate the potential using multipole expansion. I now want to evaluate that multipole expansion around for another set of particles that are some distance away. Well, I can first expand it as a Taylor expansion and evaluate that quite quickly. This all comes, this is called the fast multipole method when you do this second expansion. And Leslie Greengard has an MIT thesis which he first put all this together. And one of the things he describes in his thesis is, well, where do I stop that expansion? At what in terms of cost, or how do I optimize this expansion so that I get the best for a given error for the least cost? And he pointed out that depends on how accurate you want your forces. And so that is, the more accurate your forces means you go to higher expansion. If you don't want such accurate forces, you don't go to such a high expansion. And just some tests that I've done on force accuracy. So this is a plot of computation time. This is for, I'm trying to remember, it's about 10 to the 4 particles or so, not a very big simulant, 10 to the 4, 10 to the 5 particles. So this is the time to calculate the forces on all the particles. This is the RMS relative force error you get. And the various dots are various values of that opening criteria where I how much do I split up the particle distribution. And if we're doing quadrupole, we see that the cost versus error is a much steeper slope than the hexadecipole. So going out to 1, 2, 3, 4 terms in that expansion has a much shallower slope. And so the basic result is, if I only need forces to about 1%, then the quadrupole is fine. However, if I want forces to 0.1% or better, then I should go up higher in the expansion. And I haven't shown you the algebra for hexadecipole, but it's it's several hundred arithmetic operations. All right, so it's a bit complicated, but we can go to it if we want better efficiency. Yeah. Well, that depends on the number of particles. All right, so for 10 to the 4, I mean, it's not that much faster. For 10 to the 9, right, this is doable in a few seconds on a supercomputer. The n squared would take a lifetime to do one calculation. Okay. So, yeah, so again, this depends on the number of particles you have and say the quality of the processors you have. In practice, it's around 10 to the 5 is when people switch from going from n squared to multipole expansions. And so, for example, people doing simulations of globular clusters, okay, so this is a point where, right, contrary to what I just said here, the n is individual stars. And so you have a fixed upper bound on n, and so perhaps n squared is good enough. Generally, for people doing cosmology or hydrodynamics, you want n as big as possible, because the higher the number of particles, the more finely you're resolving your mass distribution as a continuous field. And so you're always trying to push n, and that drives you to using multipole expansions. Yeah. Okay. So the multipole expansions allow us to calculate the potential efficiently if we can separate the mass distribution into these sources and sinks that are all well separated. And so now comes the question, well, how do I take an arbitrary mass distribution and make that kind of separation? And that's where the tree data structure comes into play. So the point of tree data structures in general is to divide your computational problem into smaller pieces, and hopefully you can solve or conquer in the title there the individual pieces, and then put those solutions together. Okay, so the tree data structure is quite important in computer science. That's a quote from The Art of Computer Programming, the classical work by Donald Knuth. And simply, tree, you have a root, which is your entire computational volume or computational set, and that root has two or more children, which are themselves trees. So this is a recursive definition. So a tree is a root plus two child trees. A simple definition. Okay, and of course you repeat that recursion until you get down to what I'll call the leaves of the trees. That is, our data set, our subvolumes are now small enough that we can do the problem without going further. Now, comment about representing trees. The notes I have up here is expressed in kind of a C-like language, where I have each node has pointers to its children. This can be expressed pretty much in any language. So by pointer, I essentially mean an address in an array. So it's quite straightforward to store a tree in a linear data structure such as an array. So that's how we can put these in any language. In any language. And furthermore, right, by the definition of the tree, we're thinking of node plus children. That doesn't mean we have to organize that way in the computer. We can actually have the children know about their parents, not the other way around. So perhaps each node has a pointer to its parent. So I referred to as parent trees, which are quite useful in certain applications. And then those of you who are familiar with it, heap data structure, which is very useful for sorting and maintaining priority queues, is also essentially a tree. And that has the advantage of basically your place in this linear array uniquely identifies exactly where you are in the tree. Okay, and the bottom line here, right? Tree data structures are used all over the place in computer science. Quicksort is a great example, right? How do you sort a set of particles? Well, let's pick one particle and then use its value to divide the rest of the particles into a lower half and an upper half. And then you take each of those halves, choose another split point, divide those particles into their upper and lower points, and so on until you get down to a handful of items, sort those items, and then everything is sorted. Okay, so that's trees in general. Trees to divide up a computational domain. Well, there's several ways to do this. One way to do this is referred to as orthogonal recursive bisection. Probably it's easiest to show here. So I've got a collection of particles that I want to divide into subspaces. Well, I start by sorting well, I don't have to sort them, but I find the median particle in the x direction. Well, it happens to be this particle down here. And I divide the rest of the particles to be either less than or greater than that particle in x. And then for each of those subdomains, well, I go in the orthogonal direction, that would be the y direction, and find the median particle, the particles on the left half here, and that's this particle here, and divide them equally, so there's an equal number of particles above and below that particle. And then again, recurse again in the x direction, find the median particle, and split them, and do that with all the subdomains. And also, for the sake of efficiency, I'll choose a division that reduces the longest axis of the particles. And particularly with gravity, we want the cells to be as compact as possible, because we wanted to remember we want to reduce that x prime max of x prime. If you remember the multipole expansion, we might want to make that as small as possible, and therefore you're always trying to reduce the longest axis. Okay. And speaking of which, if we have this is actually from cosmology again, and we have a dark matter halo. We can see that there's an issue with orthogonal recursive bisection if we have a very centrally concentrated collection of particles. What tends to happen, well, the first couple splits look okay. We get nice, even domains. But I take my next split, which was, I guess it was this one here. That is, there are a lot more particles close to the center than there are out here. And that means the median particle is actually very close to the midplane, right? And so I divide that up, and now I make another cut in the y direction, and I have the same problem. And I keep going, and notice that I'm always making these cuts that are trying to include particles towards the center of the simulation. And the size of my cells, although it's getting smaller, it's not getting smaller very quickly. And so that means, for example, the multipole expansion of this box here does not converge very quickly because the size of the box is nearly the size of the simulation. So, so this is not the ideal, at least in certain circumstances, this is not the ideal structure for doing gravity calculations. Nevertheless, it does have some advantages. Because you exactly evenly divide the particles, you go down to the same level of the tree no matter where you are in space. Okay, and so this is referred to as a balanced tree. You have an equal number of nodes on the right as you do on the left, and therefore it's very easy to organize in a simple array. You have an array of nodes. If you're considering node n in the array, you can just multiply your array index by 2, and you get your children. Multiply your array index, your first child. You multiply your array index by 2 and add 1, and then you get your second child. So right. So you have the root at the start of the array. The next two indices are the two children of root. Okay. The next two indices after that are the children of the first child of root. After that are the children of the second child of root. Okay, so is that making sense? And so you can easily descend the tree or ascend the tree. You find your parent by dividing your index by 2. And so no need to chase pointers. If you know your array index, you know exactly where you are and who your parent is, your grandparent, and all the way back to the root. So this is what makes a balanced tree easy to work with. However, perhaps getting a balanced tree that also works efficiently for gravity is perhaps not so straightforward. Here's a tree that is used quite ubiquitously for gravity. It was first proposed for gravity by Josh Barnes and Pete Hutt back in 1986. And that was essentially the start of using tree codes in astrophysics. And I'm sorry, my PowerPoint skills aren't great. These are meant to be all squares here. Getting things to snap to the grid. I'm sorry about that. But I think you get the idea, is that if I start out with a square or cubical mass distribution, if I cut it exactly into 4 pieces or 8 pieces, if we're, and that hence the name oct, 8 pieces if I'm in 3-dimensional space, then each of those pieces will also be exactly square. Okay? And this addresses the problem that I showed you a couple slides back. Each division cuts that x max exactly in half. And so as I go down the tree, I am consistently making the cells smaller and smaller spatially, such that the multipole expansions, for example, for this cell, converges quickly for if we try to evaluate it on the other half of the computational domain. Okay, and furthermore, the cells are nearly spherical. Okay, so that there's not a preferred direction, but you give up the balanced. Okay, as you sort of see here, if I were to take that centrally concentrated mass distribution, I'm going to have a very deep tree close to the origin and a very shallow tree away from the origin. So you give up that balance. Okay, questions about this? So nearly all gravity codes use this kind of tree, so make sure you understand it. All right, so again, here's the root. It has 4 children. Each of the children has 4 children. Some of the children have 4 children, and so on.
Tom, I have a question.
Yeah.
I've always wondered, in this representation, all right, maybe it isn't such a problem if you're simulating a periodic domain, or if you're simulating something with, where like a fluid is gravitationally bound. But suppose I wanted to simulate, say, a galaxy, where stars may wander off. Do I get problems where, when I spatially divide, I've got one star that's gone way the hell off by itself, and as a result, my spatial division winds up putting that one star here and saying the rest of the in the other cell.
Right? It can be a problem, all right? So the first thing, yeah, so, no, that's a very good question. So, circumstance you're describing, what would end up happening is, first of all, you have to construct your computational domain so that it will include that one lonely star. And so what does that mean? Well, your galaxy will be down here, the lonely star will be up here, and so what happens is, well, you'll make a lot of divisions to resolve your galaxy just to have that one star. So the tree will handle it. There's a slight inefficiency because you're doing a few extra
Pointer resolution. You have to resolve a few more pointers.
Yeah, right. Yeah, you got to chase a few more pointers right? But fortunately, since it's, the depth of the tree is sort of is logarithmic, you're just adding a couple of steps, all right? So efficiency goes down a little bit, but it can handle it. Yeah, good question. So speaking of handling funny geometries, one tree, and this is a tree that gasoline uses, is something we call a spatial binary tree. And it's sort of a hybrid of the first tree I described, which I didn't give the name. It's generally called a KD tree, that balanced, haven't had enough coffee. Orthogonal recursive bisection tree is also referred to as a KD tree, where the K refers to the number of dimensions. So this one is a mix between that one and the OCT tree, where we don't evenly bisect it either by particle number or by space, but what we do is we bisect the longest dimension spatially. So that is, all right, so the first cut is kind of degenerate because we have a cubical boundary. But then once we, say, split it in half, we will always split, so we've got a cell like this, we'll always split it so that the longest dimension gets reduced. That means it does not necessarily balance the number of particles, but it constantly reduces the cell size. Furthermore, it's a bit more adaptive to the actual particle distribution. And this is relevant to protoplanetary disks. If all my particles are in a disk, and I do a Barnes-Hutt decomposition, well, the first thing I do is, well, I split the disk in X, I split the disk in Y, but now I have to split the disk in Z. And that means I've got sort of particles above the plane and particles below the plane are in two separate cells. Not necessarily the most efficient. It would be better if I continued to split the tree in X and Y until my cell size is comparable to the scale height of the disk. Okay? And so that's a slightly more efficient way. And again, it's the Barnes-Hutt tree does okay, but you're adding a few more steps to the tree by cutting in the Z plane when it's not really reducing the size of the cells. Okay, you understand what I'm getting at there? And so this method would tend to cut up the disk in X and Y for quite a bit until you get down to when the cell size is comparable to your scale height. Okay, but again, it's not balanced. Okay, so there is a data structure. I've told you about multipole expansions. Let's put the two together into algorithm to calculate gravity. And so the tree does the hierarchical division of space into cells. And the force on a given particle will be calculated by its interaction with a subset of those cells. And it will be that subset of the cells for which the multipole expansion is valid. That is, cells that are sufficiently small and or far away. And if a cell does not sort of satisfy the multipole criterion, well, then I take the children of that cell. All right? And so that way, for a given particle, I choose those cells which satisfy the opening criterion, that is the multipole convergence criteria, and which also tile space, right? So that I'm including all the space in the interaction. Of course, if I go down far enough, I get to the leaf of the tree and I still haven't satisfied the opening criteria, well, then I can just do the sum over the individual particles. Okay, so that's the basic outline of how you do a force calculation with a tree. A little more visually, let's see if this works. So I'm going to get out here so I can point at things. So here's my representation of the tree spatially. The root node is here. I've got 4 children of the root, are these 4 children. You can see the yellow lines here can refer to the yellow lines, and in the center we go all the way down to these green cells. Okay, and so I asked the question, I want to calculate the force of the particles in this orange cell, and due to all the rest of the matter in the computational volume, well, in calculating the force here, the multipole expansion of this red cell, rather large node, will converge. So I only need to consider the multipole expansion. I don't need to consider the individual particles. And so I essentially traverse the tree. So for this particle, I'll start at the root node. Well, the root node obviously doesn't satisfy the opening criteria because I'm inside the node. And so I look at the 4 children, and which one is it? This particular child, that is that red node, is actually far enough away that it satisfies the multipole criterion, and therefore I don't have to look at all these children. I just consider the force here. But over here, right, I'm going to have to subdivide this node into its 4 children and perhaps open this cell's 4 children. And perhaps some of these nodes will satisfy the opening criterion. And so you recursively do that, and you'll select, first that red node. Some of these nodes satisfy the criteria. The nodes up here are here. So you see that all the red here are the cells that satisfy the opening criterion. So when calculating the force on this particle, I just sum the multipoles of all these nodes indicated in red. Okay? And you can see you save calculating further down the tree when you're far enough away from the particle in question. Okay? So that's just a quick overview of how the tree walk works. Yeah?
When you set up a tree, how do you decide which nodes get further from the like a density?
Well, so you don't want nodes to be empty, right? So we generally stop dividing the tree when we get to a certain number of particles. Practically, this means 8, 12 or so. Although it does depend on your computational architecture. I'll be talking a little bit about GPU codes in a couple days. And because the floating point is so fast on a GPU, doing more particles at once helps, and so maybe you want hundreds of particles at the bottom because you can do them so quickly. But anyway, you stop dividing the tree when a node contains less than, we refer to these as buckets, a certain number of particles in a bucket. And, right, and it's not one, well, it could be one, but one tends to be very inefficient because, once you get this collection of interactions, applying to multiple particles at once takes advantage of your CPU architecture. Okay, yeah, thank you. I meant to mention that. Any other questions about this? Yeah.
So first, you build the tree everywhere, and then you traverse the tree that's necessary to calculate gravity.
Yeah. So there's two steps here. There's building a tree, which I sort of described, and now once you have the tree, you calculate it using this algorithm. Good. Yes. That depends on which tree structure you use. So if you use the KD or the ORB, orthogonal recursive, I'll get this right once, orthogonal recursive bisection tree, then you have equal number of particles. If you have the Barnes-Hut tree, then that's sort of equal space. And I hope I gave you a flavor. There's a certain trade-off of using one or another, and maybe in certain circumstances you want to use one rather than the other. This is just another efficiency. I should point out that once you know, you've constructed your tree and you know the size of your nodes, one way to think about this opening criteria is that for each node that you have, the open criteria gives you a radius for which you know your multipole expansions are valid. And what does that help you do? So when you walk the tree, the only test you have to do is the cell I'm considering, or the particle I'm considering, inside or outside that opening, inside this radius. If it is, you know you have to open the cell. If it's not, you know you can consider that cell just as its multipole expansion. Time is getting on, so this is just an efficiency thing, so I'm going to skip it and go to the next thing, which is the other use for the tree is finding your neighbor. So I'll talk about SPH in a little bit, but SPH requires knowing who your neighbors are. All right. So the Pharisees' question to Jesus, who is my neighbor? And we can find that by using the tree. In fact, that KD tree that I first described is an extremely efficient way of locating neighbors. And the way you do that is you descend a tree keeping what's called a priority queue. So we have a collection of, say, neighbors, and of that collection, we know the furthest neighbor. And so we use the radius of that collection and see if that radius intersects any of the surrounding tree nodes. If it does, then I look at the particles within that tree node and perhaps replace them if they're closer than the particles I have. And generally what you do is you start with a collection of particles in your bucket, and then you look at your sibling to see if any of those particles are closer, and then you look at your parent sibling, your uncle, to see if any particles are there and are closer. If it is, then you have to open up your uncle and look at his children, your cousins. Okay, and then you keep going up the tree that way. Constantly looking in this search ball for nodes that intersect it. As well as who is my neighbor, you might need to know, well, for whom am I a neighbor? And you can also consider use the tree for that. This is useful if you only want to find forces on a subset of particles, and I'll explain that in a second when I go to SPH, which I think I need to go on to as I'm running. I was going to talk about periodic boundary conditions, but let's not. Okay, so just a quick overview of calculating gravitational forces. We build the tree. We calculate multipole moments of all the cells in that tree. And that can be done actually by starting with the particles at the leaves. And there are methods of combining two multipoles. So if you have child multipoles, you can combine them into a parent. Do that going up the tree. And then once you've got all that constructed, then you walk the tree for each individual particle, calculating forces. That tree walk gives you both cells that you interact with and, of course, the nearby particles that you interact with, which you sum to get all the forces. Okay. I'll just right. So I started early, so I could keep going, right?
Yeah. So you started. Yes, you started early. You've gone for about an hour. On the other hand, food won't actually appear for a little while. So why don't you take another 10, 15 minutes, and that'll still get us done early.
Okay.
And you can get through SPH.
Right. Yeah, get into SPH. Yeah. All right. So yeah, I really want to get into that. You guys are doing okay with very little food on your stomachs. I'm barely staying awake here, so I hope you guys are doing okay. Well, I've got jet lag. I just came from Germany the day before yesterday, so please excuse my lapses here. I want to say a couple words about time stepping. Let me just say it quickly here, because yeah. So there's a time step. Yeah, let me not go into too much detail here, but let me just say that my favorite time step algorithm. I've got these forces. I actually have to integrate particle trajectories. How do I move the particles forward in time? A very simple scheme is one referred to as leapfrog. And it's called leapfrog because you first, let's say you have your particles and their velocities. You first move the particles using a constant velocity. And then at this new position, halfway through the time step, you calculate the forces which depend on the particle positions at that point. And you use those forces to advance the particle, the velocities, a full time step. Okay? And now you use those velocities to advance the particle positions, another full time step, use the new positions to calculate forces. And so that's the leap in leapfrog there, where you're advancing the velocities and advancing the positions are actually half a time step off of each other. Okay, it's a second order method. It's very low order, which makes it fast to calculate, but it has a particular property where it's called symplectic, in that it can conserve certain approximate quantities exactly. And just to give you a picture of how that works, here's leapfrog on a Kepler orbit. So I just got an elliptical orbit, and I'm following around the sun. Here's the radius of my, let's call it a planet, and here's the radial velocity of the planet. The exact solution is the solid line. Okay. The squares there are the leapfrog method that I just described. And then the x's are a fourth order Runge-Kutta method with the same time step. And you first think that Runge-Kutta is more accurate. Well, it is, except it doesn't exactly conserve an energy-like quantity, and so you tend to get this radial drift, which leapfrog doesn't give you. So leapfrog, although it's a simple method, is very useful, particularly if you're doing long-term integrations. like you might do in planetesimal dynamics. And I've got an example here specifically for ring dynamics, where if you use a particular type, a leapfrog type algorithm, you can, here's the leapfrog type algorithm conserves this, in this case, the eccentricity, whereas using a more standard Runge-Kutta type algorithm, you're growing the eccentricity, which shouldn't happen. Let me take some time to get into SPH here. Well, before I do that, let me talk about gravitational softening, since it came up here. Right, so there's that sum again. And we recognize that one way to think of the evaluating that potential is that your particles are this Monte Carlo sample of your density distribution. But with that 1 over r term, my estimate of the potential is badly wrong when x equals x prime. And so that's why we put the softening in, so that our estimate of the potential is a little closer to the sort of the real potential, even when x equals x prime. Now, there's some, so you're minimizing the force error. But the fact that we can't resolve forces down to arbitrarily small distances now means that we have to think hard about what happens on the very small scales. And this becomes a problem when we're thinking of self-gravitating fluids. We need to resolve what's called the Jeans length. And this is a point where the pressure support can overcome the gravitational force. So the pressure support is given by the sound speed squared. Gravitational dynamics is given by 1 over g rho naught. And so the Jeans length is the ratio of those two. We need sufficient particle resolution that we can resolve this. And if we don't, well, the statement here is you're not doing hydro. Okay, so if you're not resolving the Jeans length, then you have this self-gravitating fluid for which you're not calculating the pressure support correctly, and who knows what's happening. For a cosmologist, what I say is happening, star formation is happening there, okay? But that's not hydrodynamics, right? That is saying, okay, I've got a prescription. If that parcel of gas goes Jeans unstable, well, then it's collapsing to form stars. But that's something that's happening below the resolution of my calculation. Okay, so with that, I'll take a couple minutes to get into smooth particle hydrodynamics. And just why I use smooth particle hydrodynamics before I describe what it is. All right, so I'm using particles again to characterize not just the collisionless fluid, but gas. And that naturally partners with an n-body simulation. It's a Lagrangian technique. That means that particles contain the mass, and so the advection is always perfect. I always know where my mass is going, and that can be an advantage. By Galilean invariant, there's no, it's not, the absolute value of the velocities don't matter, just relative velocities. This is particularly important, if I have a parcel of gas going around the galaxy at 200 kilometers per second, but its sound speed is only 10 kilometers per second. It's important that I can essentially take out that galactic rotation. I'm going to go, well, just a few other advantages. Quite easy to implement, and there's a certain flexibility. It's a low-order scheme, and so there's a flexibility with the equation of state that you don't have when you have more complicated equation of state solvers like Riemann solvers. So given that, let me just go over what you do. So again, fluid is a collection of particles. The form of the hydro equations are the Lagrangian form. That is, you're calculating this time pressure gradient forces on the particles, and that is moving the particles to their new positions. As well as density, the particles also have other thermodynamic quantities, for example, entropy or internal energy, which you evolve as well. But some of those particles are not, some of those attributes are not determined on an individual particle, but they're determined by taking an average over the nearby particles. Things like pressure and density are sums over nearby particles, and that's done using an interpolation technique. And so here's the basic idea of interpolating a field. That is, I have a collection of particles, so I know these quantities exactly only at particular points. How do I determine those same properties at an arbitrary point in space? Well, I can make a guess or interpolate the values from individual points by doing this integral over the points that I know using a weighting function. It's just a function of the separation between where I am and where I know where the particles are. All right, and this weighting function is characterized by a smoothing length, which will probably be also the order of the gravitational softening. And then this kernel is just a weighting kernel such that its integral is 1, and it's a delta sequence that as h gets small, it approaches a delta function. Okay, so that's how you get a interpolate quantities from particles. And since we have particles, that integral I showed you on the previous slide turns into a sum of the forces multiplied by the weighting function divided by the mean volume density of those particles. And in particular, I can make an estimate of the density at an arbitrary point by simply summing the masses times the weighting function over nearby particles. So this is sort of the basic formula of SPH. I can turn particles with masses into an estimate of the density. Okay? But we need to calculate, actually, we not only need to calculate fields, we need to calculate derivatives of the fields. That is, in hydrodynamics, the force is the gradient of the pressure. So how do I do gradient of a delta function sort of thing? Well, you can actually, right, we wanted grad f here, but I can use integration by parts to move the gradient from the f to the gradient of the weighting function. Okay? So I get the gradient of my interpolated gradient of f by doing the sum using the gradient of the weighting function. Okay? So questions here. So this is sort of the basic idea that allows you to express Euler's equation using a collection of particles. So I want to make sure that's clear. All right, so I know some quantities only on particles. I can use those using a sum of neighbors to get interpolation of those quantities at arbitrary points in space. And furthermore, I can also interpolate the gradient of that quantity at arbitrary points in space. Okay?
So I'll ask a question of this that I always wondered.
Yeah.
So suppose that I have a point that is a point in space that is on a caustic between two different sets of neighbors. That is, if I move a distance epsilon from my current position, then someone who's currently in my neighbor list will fall off it, and someone who is not in my neighbor list will enter it. Does its derivative therefore become undefined at that point?
Well, generally, the weighting function is such that its second derivative, its second derivative is continuous, so it's going to 0. So as that new neighbor comes onto your neighbor list, it comes on with a very small weighting, right?
Okay.
That continuously goes from 0 to a finite value.
Okay, so the way you avoid having that discontinuity is by choosing a weighting function such that grad W goes to 0 for the most distant neighbor.
Yes.
Okay.
Yeah. That doesn't mean that that's still not an issue. Okay, yeah, right. Contact discontinuities are a subject of recent debate and discussion among SPH implementers. But the basic question you ask is solved by having an appropriate weighting function. Okay. Yeah. Yeah. The weighting function, right? Right? You want continuous second derivatives first of all, for the reason that Mark pointed out. When you take that gradient, you want it to be smooth as you change your neighbors. Another thing you would like is for the weighting function to be compact. That is, if your weighting function were a Gaussian, which you'd think would be the most natural thing, well, a Gaussian extends out to infinity, so that sum you would have to do would be over every entire particle in the simulation, and then back to n squared, and that'd be computationally impossible. And the other thing you want the weighting function, you want the forces to be symmetric. That is, Newton's third law is a very good idea. It expresses conservation of momentum, and therefore you want the force of I on J to be equal to the force of J on I. And so you want your smoothing function to express that. And the way we do it, you can see that we use a cubic spline, so that will have the continuous second derivatives, and it'll be compact. And the symmetrization we do by explicitly. When we calculate a force, we make sure that we add the negative value of that force to the particle we're calculating it from. Another thing that the weighting function has to do, the pressure, not only, and this is a funny thing about SPH, those pressure forces, of course, you want to solve Euler's equation, hydrodynamics, but you also want those pressure forces to maintain your particles in this uniform distribution. And so you have to be a little bit careful of what happens to the force as the separation goes to 0, because you don't want your particles to fall into each other, all right, and make a very clustered distribution. You want an even distribution of particles, and that's something to watch out for in smooth particle hydrodynamics. Let me just, you find a neighbor. I told you that you can use the tree to find the neighbors. And so let me just, let's see, I'm about an hour and 13, so just a couple more slides, and then let you guys take a break. So putting all that together, here's your equations of SPH. Because mass is exactly conserved, I do not need to solve the continuity equation. Mass just follows the particles. I don't lose or gain mass, ever. So we just need to estimate the density at each time step. Once I know the density, I can solve Euler's equation, which is saying that the acceleration is due to the pressure forces, and I should actually put a grad phi out here as well. I forgot. All right, there's gravity involved. There would be a gravitational force as well. But you can see it's a gradient of the weighting function, and we have the pressure expressed in this form, which I didn't really have time to go over why you get this. There will be an artificial viscosity term, which for SPH has to be put in explicitly. to stabilize the equations of motion. This is in contrast to most grid codes where there is the way you write down your difference equations, make sure you stabilize the integration of Euler's equation. SPH, you have to put that down explicitly, and I'll talk a little bit more in the next slide. And then you have the thermal energy equation or the entropy equation. Here, if you're solving thermal energy, you have to keep track of the PDV work, so the energy you get by expansion or contraction, and that's given by the relative velocities. Or you can solve the entropy equation, in which case you don't need to include this term. But if you have cooling or other radiative processes going on, you're going to have to include a cooling term here. And that gets a little more complicated if you have an entropy equation. And then just another word about artificial viscosity. So even if you have a situation where you have no heating or cooling, the entropy of your gas can change because you have shocks and things like that. And so you need something in the equations which will turn the kinetic energy of the gas into thermal energy, as what happens in a shock, and that will happen through artificial viscosity. And we have actually two terms, and it's actually the second quadratic term. Sorry, this mu gives you an idea of how fast particles are approaching each other, okay? And so there's a term that scales with the square of the approach velocity. And for you have a strongly convergence flow, as happens with shocks, and you want a term there will turn that convergent flow into thermal energy. But we also need this linear term, and this is again stabilizing the particle positions. We want our particles to smoothly represent our fluid, and so there's a linear term in here. Sorry, an alpha term that goes linearly with the flow, if the flow is converging. Okay, so and again, as I mentioned in answer to Mark's question, there's a lot of debate about how big these terms ought to be. But think of it, right? To stabilize Euler's equation, you need some form of dissipation. SPH doesn't have an explicit or an implicit dissipation term. You have to add it explicitly, and it's done by this artificial viscosity. Okay, so I think I've bored you enough. Let me just review, right? So SPH, it's this low-order method. There's no issues of Riemann solvers in advecting the flow from one particle to the next. It's so low order that you do the exercise of taking the gradient of 1, and you won't get 0. So this bothers some people, as I guess it should. And generally, you have errors of that sort when the particle distribution gets funny. And usually, in a grid code, if such a situation happens, the code will crash. In SPH, it just keeps going and just gives you garbage for answers. Sorry, question? So, right, you have a smooth distribution of gas, and you would like the particles to be roughly evenly distributed throughout space. But you can get situations where you get particles for some reason or another artificially cluster on you, and that's kind of bad. Okay, another way to think of it, if we put down particles in a Poisson distribution, the error goes as the square root of n, 1 over the square root of n, which is not very good. If you can put your particles down in a more uniform distribution, then your error goes down as 1 over n. which is much better. And so you want that 1 over n dependence on error, not 1 over square root of n. All right, and that's and sometimes this can happen if you have a bad kernel that causes a clumping instability. Okay. Okay, I think that's oh yeah, gosh, break for coffee. I did the full hour. Hour and plus.
All right, thank you.
Yeah.